Welcome to getting to know more about the scientific method and experimental design than you ever thought you would. Let's start out with a couple of pieces of terminology. Observation. This is something that you can tell by your five senses. This means something like, gosh, I smell something burning, or wow, that really tastes bitter. Inference. This is an educated guess based on environmental evidence. If I walk into the room and I see a yellow spot on the ground and I have a dog, my logical conclusion is going to be that my puppy isn't house trained yet, he went on the floor. That's an educated guess or an inference. Quantitative. Quantitative is an observation or inference that uses numbers. For example, I observe 3 birds on a railing. Inference. I infer that that man had 20 ounces of coffee because that's how much it looks like he has on his shirt. Qualitative. Qualitative is an observation or an inference that does not use numbers but instead uses qualities. I saw a beautiful rainbow that had, all of the colors of the spectrum. Red was the best. Another example might be, I heard a bird singing in the tree. Its song went very high and very low. You can also turn observations from quantitative to qualitative or from qualitative to quantitative. Please just keep in mind things like the letter A, meaning an object, or a dog. That's not a number value. You need to use 1 or 2 or 10 or 0.5. Just make sure you get an actual number in there. Terminology continued. Independent variable. The independent variable is the one that the experimenter decides to change. The dependent variable is not changed by the experimenter. It depends on what the experimenter chose in the independent variable. In other words, it depends on changes in the independent. Constants. Ideally, this should be everything else in the experiment. Your idea should be to keep everything as similar as possible. Now, I'm going to be honest with you. As you get older and when you get into a lab setting, if you're doing complex experiments, sometimes there will be more than one factor has changed. But for us, in 9th grade honors environmental science, we're going to strive very hard to change one factor, keep everything else constant, and then look for that change in the dependent variable to see if indeed our change in the independent causes the change in the dependent. Hypothesis. It's an educated guess. I like to have you put it in the if-then format for simple experiments in class because that way you always know where the independent and the dependent variable go. If you think about the experiment and you logically try to explain it in an if-then format, you will always put the independent variable first and the dependent variable second. There are other ways to write hypotheses, many of them, but I show you this format in the hopes that it will help you as you become more comfortable with independent and dependent variable. Experimental design. An experiment deliberately imposes something upon a treatment group. This means that we select an independent variable and we actively engage a group of objects or people or organisms with that independent variable. There are many ways to do an experiment, but sometimes experiments get crossed over with observational studies. They are both incredibly valid ways of doing science. An observational study means that a lot of times anthropologists use this. You go to a place and you observe a group of people. For example, let's just say that you're really fascinated by Japan and you want to know what it takes to become, a sushi chef in a very competitive environment. So you simply go, to some of the top sushi restaurants in Japan. You take notes on what it takes to become a sushi chef. That's an observational study. You don't impose things on the environment, you observe the environment. When we do an experiment, we deliberately impose something upon a group, and then we look for the results. Experimental design. Experiments need to generate data, and they need to generate the right type of data and enough data. I'm not sure if your science teachers in the past have told you, but at the level that we're at, usually we say 100 pieces of data is a pretty solid experiment. That means you have to collect 100 pieces of data and analyze it to know whether or not the treatment that you placed on the experiment, or that independent variable, is actually causing the outcome that you're seeing in the dependent variable. This is experimental design. Sometimes you guys call it the scientific method. Treatment. A treatment is something that researchers administer to experimental units. For example, my experimental units are going to be corn plants. I treat them with different types of fertilizer, and I see the outcome in their corn production. Now, sometimes when we do experiments, the experimenter can get in the way. So this is called experimental bias. And this is really hard to overcome if you're just doing a plain experiment. For example, let's say that I was trying to investigate police shootings. And I go in and I interview these particular cops. And let's say that one of the cops says something that I don't agree with. Well, now I'm biased against him, and now I read into the other things that he says. Whenever possible, we need to make sure that the doctor or the scientists that is imposing the treatment does not allow their personal values to get in the way of what the results end up being. There are a lot of ways to do this. We're going to look at two ways to do it on the next slide. The placebo effect affects the other end, the people receiving the treatment. If people know that they are receiving treatment, they often feel better, even if the medicine is not actually causing that. Sometimes simply seeing a psychiatrist or seeing a doctor, or even just having a friend, someone there to hold your hand, ends up making you feel better. That's the placebo effect. And while that's all well and good, if we actually want to lower the heart rate, or regulate the heart rate of a patient, we need to know that we can do that not for one patient, but for all the patients. And so managing the placebo effect is really important. Is the pill I gave you fixing your heart, or is the fact that I, a doctor, am giving it fixing the problem temporarily? Ways to eliminate these sources of bias that I just talked about. There's a thing called a double-blind experiment. In this experiment, neither the person giving the treatment nor the people receiving the treatment are aware of what group they're in. So the simplest example is, when I hand you a little white pill, is that little white pill filled with sugar, or is that little white pill filled with medicine? When you take it and you fill out your survey, I, the person giving it to you, don't know, and you, the person receiving it, don't know. So the hope is that when we get your data or your feedback, when we look at your lab results, we're going to get a really honest opinion from people who don't know what group you are in, whether or not the medicine is actually helping these 10,000 people. Placebo effect. Again, the placebo effect is controlled by ensuring that the people involved in the back end of the study don't know what group they're in. If you don't know what group you're in, then it's harder to be biased and to say, oh, I must be feeling better because I'm receiving the medicine, because you don't know whether you are or not. So again, you're a little bit more honest. How am I really feeling? Do I feel better than yesterday? Is this medicine really helping me to recover? Another ways to eliminate sources of variability and bias, randomization. when you're creating your groups, it's really important to randomize how you create your groups. A lot of times humans think that even distribution is randomization, but it's really not. So essentially, when people sign up for a study, you make sure that a computer does the sorting so that you get an unbiased, completely random sorting of gender or race or age or, you know, back or monetary background, so that when you impose the treatment, you're imposing the treatment on equal groups, and that those equal groups are giving you equal feedback. Replication is probably the most important. What that means is that I here at LA University do an experiment, which I then pass off to Stanford that does the experiment, which then passes it off to the University of Iowa that does the experiment. And if we all get similar results, if that thing that I've created, if that treatment and on the experimental data that I've created, if other people can replicate it, then we know that it's most likely my independent variable is causing the change that I see in my dependent variable. Again, think back to the autism thing. One man did one bad experiment where we said that vaccines cause autism, and to this day, people still can't get that out of their mind. That study was never repeatable and in fact was completely debunked, thereby showing how important replication can be. Here are the basic steps of the scientific method. We're going to do some labs and some fun activities that work your way through this. I know that this is something that you've seen before, but I hope that the stuff that was presented prior helps you to understand why what seems like a very simple construct is actually really hard to get right.